Welcome everybody to our Gamma seminar. Today we have the pleasure to guest Bartosz Zawora from the University of Warsaw. He's going to talk about an introduction to the energy momentum method. So Bartosz, the floor is yours. Thank you for accepting our invitations.
Thank you very much, and I would like to thank the organizers for inviting me. And yes, today I would like to present an introduction to the energy momentum method. So what is the basically what is the energy momentum method? So the classical energy momentum method is a technique that allows for analyzing the stability of Hamiltonian systems on symplectic manifolds that admit some particular symmetries, Lie symmetries. The energy momentum method utilizes the Marsden Meyer Weinstein reduction, which means that we will deal with particular equilibrium points, the so-called relative equilibrium points, but that are not necessarily the critical points of the initial Hamiltonian, but are critical points of the reduced Hamiltonian. But I will talk about it in detail later. So the classical energy momentum method, as I said, was devised on symplectic manifolds and was devised and developed by Juan Carlos Simo and Gerald Eldon Marsden in 1988 in the paper entitled The Energy Momentum Method. So on the left, we see the Juan Carlos Simo, passed away in 1994, and Gerald Eldon Marsden, who passed away in 2010. So they are the authors of the classical energy momentum method on symplectic manifolds. Okay, so the structure of the talk is as follows. First, I will recall you. Yep.
Yes, a comment, because the energy momentum method was something that it was related to something called the energy Casimir method, yeah? Could you comment
yes.
on it and how it comes? Because maybe it had lots of applications and it was quite important.
Yeah, I will comment on some generalizations and significant applications at the end of my talk. And then I will also talk about the energy Casimir method. So let's postpone it.
Okay.
And so as I said, the structure of a talk is that first I will recall the basic definitions from symplectic geometry and Poisson geometry. Then I will shortly present the Marsden Meyer Weinstein reduction, and then I will move to the energy momentum method, which is the main interest in this talk. So as I said, the first definition, since the classical energy momentum method is defined on a symplectic manifold. So a symplectic manifold is a pair P omega, where omega is a differential two form that is closed and non-degenerate. And then I will call the pair P omega a symplectic manifold. So of course, on a symplectic manifolds, we can define a vector fields, Hamiltonian vector fields, which are the vector fields that contraction omega with this vector field is a differential of some function f, and then f is a Hamiltonian function of a vector field x. Then we have a map from C infinity, I mean set of smooth functions P times the set of smooth function to the set of smooth functions, and P is a Poisson bracket. If this pair is a Lie algebra, and moreover, the map, this map satisfies the Leibniz rule for every function f. And remarkably, every symplectic manifolds induces a Poisson bracket on the set of smooth functions on this manifold, and this Poisson bracket is given as follows: that the Poisson bracket of functions f and g is a symplectic form taken on the associated Hamiltonian vector fields with those functions. Okay, So then we have the map from the set of smooth functions on a manifold P to the set of vector fields is a Lie algebra morphism, where the Lie algebra on the left is given by the Poisson bracket, and on the right is given by the commutator of the vector fields. So, as I already told you, we'll deal with the Lie group actions, Lie symmetries. So we will be concerned with fundamental vector fields that are basically vector fields tangent to the orbit generated by a Lie group. And the fundamental vector fields are defined as follows: that this is a vector field which is given by d over dt at t equals 0. And here we have the Lie group action. And in the first argument, we have the exponential map of t xi, where xi is an element of the algebra and some point p in a manifold, right? So again, these are the vector fields that are tangent to the orbits generated by a Lie group G. We will be also interested in a symplectic momentum maps that are so-called adequivariant. I will move to that later. But to define it, we need the definition of an adjoint action. So it's a Lie group action on a Lie algebra G of the following form. And this is basically the left multiplication by G and right multiplication by G to -1. And it's the tangent map to this composition, right, for an element in the algebra. And we defined also coadjoint action, which is just a dual to the adjoint action. And basically we'll be concerned with this coadjoint action, basically. Okay, so now we have to define the symplectic momentum map, which play an essential role, first of all, in the Marsden Meyer Weinstein reduction, and then in the energy momentum method. They're very important since, as we will see later, the dynamics is basically contained in the level sets of the symplectic momentum map. So what is a symplectic momentum map? This is a symplectic momentum map is associated with Lie group action on a symplectic manifold, and this is a map from the symplectic manifold to dual to the Lie algebra, and it's defined as follows: that the contraction of omega with respect to the fundamental vector field is given by the external derivative of the momentum map paired with xi, where these triangle brackets denote the natural pairing between G and G star. So this is the definition of the momentum map. And as I told you, we'll be focused on adequivariant momentum maps, which are momentum maps satisfying the property that this diagram commutes. Okay, so it means that the composition momentum map composed with the coadjoint action of G to -1 is basically the momentum map composed with Lie group action for every element in a Lie group. So on the picture, just to help you illustrate the concept of adequivariant symplectic momentum maps, we have two level sets of the momentum map. We have a Lie group, orbit of a Lie group action that sort of connects these two level sets, and that the idea is that if we apply the momentum map to this level set, we get a mu prime. If we apply the momentum map to this level set, we get mu, and mu is related to mu prime with the coadjoint action of G to -1. So this is the idea. And at this point, it's worth noting that in general, we don't have to assume, it may happen that the symplectic momentum map is not ad equivariant. But the thing is that we always can make that the symplectic momentum map is equivariant, but with respect to other action on G star. Okay, so it's quite technical, but the conclusion is that there's always action on dual Lie algebra, Lie group action, that makes the symplectic momentum map equivariant. And then you can apply these results to the Marsden Meyer Weinstein reduction, to the energy momentum method. And it's very, as I said, it's very technical. It changes some technical things, but the main idea and the core remains the same. Okay, so you have to, you can keep in mind that the symplectic momentum map is not always ad equivariant. That's as, for instance, in the contact case.
Sorry, Bartosz.
Yep.
To use other types of relaxing, because this is a standard Marsden Weinstein relaxing with the momentum map, yeah? And with the level sets. But have you tried how to deal then with momentum map with, for example, the reduction over the inverse image of a quad joint orbit, or using some kind of quasi-tropic reduction and things like that? Have you tried to use these techniques with the momentum, with the energy momentum method?
No, I haven't tried to use those techniques in the setting of the energy momentum method, but these are very well-known results in the setting of reduction theory and sort of things. But yeah, it's a fair point. I haven't tried it.
Do you think that it is possible?
Yeah, I think so. I mean, yeah.
Okay, thank you.
But it's, yeah, it is. I think it is. It should be. Okay. The level set of the momentum map is a submanifold of a symplectic or initial symplectic manifold. So to make sure that it's a submanifold, we require that the element mu in G star is a weak regular value, which of a symplectic momentum map, which basically means that the level set is a submanifold, and this relation holds, which is sort of natural. Then notational thing is that G with lower index mu denotes the isotropy group at mu of a Lie group action G of the quad joint action on G star, and this is the Lie subgroup that we will be quotienting by the level set of a symplectic momentum map. And to the reduction, we also need the notion of symplectic orthogonal of a vector subspace WP at some point with respect to the symplectic structure, and it's defined as the vector fields such that omega taken on WPVP is equal 0 for every vector fields, for every vectors W belonging to this vector subspace WP. So it's kind of resembles the notion of orthogonality in Riemannian setting, but it's not, it doesn't have to be orthogonal in the natural sense, since we are dealing with symplectic forms. Okay. So we are almost ready to move to the Marsden Meyer Weinstein reduction. Here is the lemma that is essential to prove the Marsden Meyer Weinstein reduction, classical one, which works for symplectic manifolds. So basically this lemma says somehow connects and shows the properties between the submanifolds tangent, the submanifolds of the symplectic, initial symplectic manifolds, and shows the relation between them. So the first item says that the intersection of the tangent space to the orbit generated by the whole group with the tangent space of the level set of a symplectic momentum map is exactly the tangent space to the orbit generated by the Lie subgroup G mu, and this is illustrated on this picture. Right here we have the whole orbit, here we have the whole level set, and the intersection is given by the orbit generated by G mu. The second thing is that the relation between the tangent space to the orbit and tangent space to the level set of a symplectic momentum map is given by this relation. So the symplectic complement of the tangent space to the whole orbit is given by the tangent space to the level set of a symplectic momentum map. Right. So in a Marsden Meyer Weinstein reduction theorem, we will need Lie symmetries. So we define a symplectic Lie group action, which is just a Lie group action that leaves our symplectic geometric structure invariant, which is given by this condition. So the pullback of omega with respect to the Lie group action, doesn't change the geometric structure, so it's equal omega for every element in a Lie group, right? So we will have we have the symmetries of our geometric structure. Second definition is a definition simplifying the notation. So from now on, a G-invariant Hamiltonian system is a 4-tuple P omega H J, where P omega is a symplectic manifold, H is a G-invariant function, Hamiltonian function, and J is an adequivariant symplectic momentum map associated with a symplectic Lie group action. And as I said before, the symplectic momentum map is invariant related to the flow of the Hamiltonian vector field of a G-invariant Hamiltonian systems, right? So the momentum map composed with the flow of the Hamiltonian vector field is just the momentum map for every parameter t, right? So if our dynamics starts from a point that is contained with the level set of the momentum map, it remains in this level set for every time. This is what it means basically. Okay, so now the symplectic Marsden Meyer Weinstein reduction theorem. So we start with a G-invariant Hamiltonian system. We require it to be a weak regular value just to make sure that the level set is a manifold. And we also assume that the Lie group action is quotientable on the level set of the symplectic momentum map by G mu, which means that the quotient of the level set by G mu is a manifold. And here it's also a space for many generalizations of this theorem. I think one of the most one of the most not important but most popular generalization is to require that the Lie group action is proper, but it's not free. Then we get the orbifold structure on the quotient space, and in the reduction theory, this is very popular condition to require that the Lie group action is only proper, for instance. Okay, so then this theorem says that we get a pair P mu, which is given by the quotient of the symplectic momentum map by G mu, is a symplectic manifold with a symplectic form omega mu, which is related to the initial symplectic structure as follows: that the pullback of omega mu with respect to the canonical projection P mu is given by the pullback of initial symplectic form with respect to the canonical immersion iota mu, which is the immersion of the level set of a symplectic momentum map to the initial manifold P, and P mu is just a projection, is the quotient map. Okay, so just this is the statement of the theorem. So on the picture, right, we have the level set of the momentum map. We have the Lie group. Their intersection is given by the generated by G mu, and the theorem says that the quotient of the level set by G mu is a symplectic manifold omega mu that and this reduced symplectic structure is inherited from the initial one, right? So this is the main idea of the Marsden Meyer Weinstein reduction. Just to find the proper quotient, so we have a symmetries, Lie group, Lie symmetries, and we want to find a quotient that is manifold and possess the same geometric structure that is inherited from the initial geometric structure. And this is the main idea of the Marsden Meyer Weinstein reduction. Okay, so we reduce the geometry. So what about the dynamics? And of course, the answer is that we can also reduce the dynamics. So we can reduce the flow of the Hamiltonian vector field. And this is the proposition that the flow, first of all, leaves the level set of the symplectic momentum map invariant, and it uses a unique flow on the reduced manifold, satisfying this. And there is also a relation between the Hamiltonian functions, the reduced Hamiltonian function, the pullback of the reduced Hamiltonian function with respect to the projection, as given by the pullback of the initial Hamiltonian function with respect to the iota mu. So again, on the picture, we have our initial dynamics, xh, since the flow leaves invariant the level set of the momentum map, the dynamics is contained in this level set, right? So we can reduce this dynamics on the quotient manifold, and we get the Hamiltonian vector field xh mu, which is the Hamiltonian vector field associated with the reduced Hamiltonian function h mu. So now the thing is, the idea of the energy momentum method is as follows. Okay, so what if there is a point at the level set of the symplectic momentum map such that the Hamiltonian function the Hamiltonian vector field is proportional to the fundamental vector field for some element in Lie algebra, right? So since the fundamental vector field, since the Hamiltonian vector field is always tangent to this level set, and at this point is equal to the fundamental vector field, it means that this fundamental vector field has to be tangent to the orbit generated by G mu. But since this Hamiltonian, we quotient by G mu, this vector field quotient to 0, right? So this means that on the reduced space, we may have a point that is equilibrium point of a reduced Hamiltonian vector field, but it's not an equilibrium point of an initial Hamiltonian vector field. So this is the motivation for considering the so-called relative equilibrium points, which I'll define in a moment. And the idea of the energy momentum method is to present some kind of algorithm, how to find these points and how to study the stability of such points. Okay, so as I, yeah.
Yes, what you said in briefly, could you say that you are studying points where the evolution of the dynamical system are given by the Lie group symmetry, yeah?
Yes, exactly.
In short, yeah. Okay.
Yeah. Yes, and I will tell you this when I move to this corollary. Yeah, exactly. But thank you. Okay, so the definition is that ZE is a relative equilibrium point of a G-invariant Hamiltonian system if there exists an element in a Lie algebra such that the Hamiltonian vector field at this point is equal the fundamental vector field at this point. But equivalently, we can say that the point ZE is a relative equilibrium point if and only if the projection of ZE is a critical point of a reduced Hamiltonian function, right? This is what I said earlier. And the corollary says that the following two conditions are equivalent. So a point ZE is a relative equilibrium point of a G-invariant Hamiltonian systems is equivalent to that every particular solution passing through this point ZE is of the following form, right? For some curve G of t in a Lie group. So this is exactly what Javi said in a moment ago, that the dynamics, that the evolution is given by a Lie group symmetry, by a curve in a Lie group G. And in fact, since the particular solution is always contained in the level set of the Hamiltonian symplectic momentum, once again, if the evolution is always contained in the level set of the symplectic momentum map, we actually conclude that this curve is not in G, it's a curve in G mu. Okay, so as I said, the idea of the energy momentum method is first of all, characterize this relative equilibrium point. So how to effectively and relatively easy find these kind of points. And second of all is to present a way to determine their stability. So we want to consider the dynamics very close to the initial one. We want to project them, right, and study whether, for instance, this projected, here we have the equilibrium point of a reduced Hamiltonian vector field, and we want to see if this point is stable or unstable, what happens with very close trajectories projected on the reduced space, if they are close by to this equilibrium points or run away, this sort of things. Okay. And the core of the energy momentum method is this theorem, which allows for characterizing the relative equilibrium points. And this theorem says that a point ZE is a relative equilibrium point if and only if there exists an element in Lie algebra such that ZE is a critical point of the hxi, which is the extended function, Hamiltonian function, and is defined in here. So now you can take a look at this and conclude that this is nothing else. This theorem is nothing else as the Lagrange multiplier theorem, written in a little bit different form, where the Lagrange multiplier is played. I mean, where the psi element in Lie algebra plays a role of the Lagrange multiplier, right? So we want to, instead of like reducing the whole system, find critical points or equilibrium points of the reduced Hamiltonian function or Hamiltonian vector field. We are looking for the critical points of the extended function defined on the initial symplectic manifold, and this is and this is one of the main advantage of the energy momentum method, since it doesn't require, like, especially in some more complicated examples, like using the whole machinery of the Marsden Meyer Weinstein reduction, which is, by the way, very nice, but in terms of computations, it may happen that it very, very quickly gets complicated and sometimes even unbearable. So the main advantage, once again, is that we don't have to compute the reduced Hamiltonian system. We just need to compute the momentum map, and to do that we need the symmetries. So okay, finding symmetries may be tricky sometimes, but if you have a symmetry, so you compute the momentum map, and basically this is all you need for finding relative equilibrium points in this classical symplectic setting. Okay, so this theorem characterizes relative equilibrium points. We know how to look for them, and it's very, I mean, sort of very easy, right? We are just looking for critical points of this function, hxi.
Bartosz, I have a question. And normally
Yep.
when you have Lagrange multipliers, you require the point. You can do it when the submanifold is defined by means of the regular point of the function. Yeah. Nevertheless, here, what are you supposing about the value of the momentum map? That this is weak regular or regular?
Yeah, I mean, I introduced the notion of weak regular value, and we just assume that mu is a weak regular value of the symplectic momentum map.
It's not exactly like the case of Lagrange multipliers, yeah, because it's weak regular. Could you explain why you can use it?
Yeah, well, basically, the thing is that to compute to use this theorem, to prove this theorem, we only need the two things that are required in definition of a weak regular value. I mean, I didn't define the notion of regular value, but we don't need to be a momentum map reactive submersion. I mean, weak regular value is it's enough to guarantee that this theorem works, which means that we need that the level set of the momentum map is given by it's a manifold, it's a submanifold of the initial manifold, and this condition that the kernel of the tangent to the symplectic momentum map is given by the tangent to the level set of the symplectic momentum map.
You notice that when you assume that this is only a weak regular point, it may happen that the function h restricted to the submanifold may have a critical value, but there is no solution of the sort you have given it here. The problem when you have the Lagrange multiplier and the submanifold, you are dealing with is not defined by means of regular points. Is that it may happen that the function you are studying has a critical point on the submanifold, yeah, but it's not retrieved by means of Lagrange multiply. But the thing is, in this case, you are not exactly concerned with Lagrange multipliers of these critical points. You are concerned with points that are generated by the infinitesimal evolution of the Lie group. And these are exactly the ones given by these functions you have in here, and they are of this sort. So this is exactly the problem you are concerned with. So this is it's a little bit subtle, yeah? That's what I am asking. It can be done, it is properly defined, but the reason is that only these points are those that are important to us. This is the thing. Okay, thank you.
Yeah, that's true. I mean, this comes from the definition of a relative equilibrium points, right? When we are concerned the points where the Hamiltonian vector field is proportional to the fundamental fundamental vector field. Yeah.
If those, we don't care. Maybe there is something that
exactly. Yeah. Thanks. Thank you for the clarification. Okay, so as I was saying, this theorem just characterized the relative equilibrium points, so we know how to find them. So now, what about the stability? So just let me recall you that the second variation of a smooth function is defined as defined here, like for every vector for every two vector fields x, y, and smooth function f, right? So if df, the exterior derivative of f, is equal to 0 at some point, certain point p, then the second variation of f taken on x and y at this point p depends only on the values of x and y, and gives rise to well-defined bilinear form on the tangent space of B at this point, right? So we are going into towards the result. I mean, we want to that what is enough to conclude that we are dealing with the formal stability is that is the studying the second variation of this extended Hamiltonian function, sorry, right? So we know how to find the relative equilibrium points using these functions. So we want to show that we can also determine whether an equilibrium point, relative equilibrium point, is stable or unstable, also using this extended Hamiltonian function. And indeed, this is the case, but we need to consider the directions. We want to examine what happens with this bilinear in directions that are tangent to the orbit of ZE generated by the G mu E, by the isotropy group at mu E. And it happens, I mean, it's correlates the second variation vanishes along those directions, which leads us to the conclusion that the formal stability of a relative equilibrium points requires positive definiteness of the second variation on the tangent space to the level set of the momentum map modulo the gauge directions, which are directions like towards the orbit generated by G mu E. Okay, so we don't need to take into account the directions that are tangent to the orbit generated by G mu. So the formal stability of a relative equilibrium points is equivalent this condition for every vector field, every vector V that belongs to S, non-zero vector field phi in S, where S is some vector subspace at the tangent of the tangent space to the level set of the symplectic momentum map that is supplementary to the tangent space to the orbit generated by G mu E. Right. So now we can. This is the energy momentum method basically, which says that we can characterize the relative equilibrium points and its stability using only the extended function h psi, and the formal stability boils down to the positive definiteness of the second variation of that function at this point for vectors in a subspace, vector subspace S. So again, if the flow is just contained in the G mu EZE, right, which is in the orbit of orbit generated by the isotropy group mu E, it projects to an equilibrium point of a reduced Hamiltonian system, and we can study the stability if the closed trajectories to the initial one run away from these equilibrium points, or we can study by this extended function h psi, and to be more precise, we just need to study the positive definiteness of that second variation and positive definiteness of that second variation of h psi. Right, so this is the main advantage of the energy, classical energy momentum method. So shortly, as a conclusion, the energy momentum method requires roughly 3 steps. So first, we need to compute the symplectic momentum map, right? So we have to have symmetries. We have to know the symplectic structure. Then we can compute the symplectic momentum map. If we know the symplectic momentum map, we can construct the extended Hamiltonian function. If we have this function, we just find relative equilibrium points as critical points of this extended Hamiltonian function. And then to determine their stability, we study the positive or negative definiteness of the second variation of this extended Hamiltonian function, right? Which is just...
Yes, one comment about this, because before the existence of this method, one of the things one could think of was just picking up the initial Hamiltonian system and looking for the Hessian and looking for stability of the function of the Hamiltonian function of the problem. But the problem is that when there are symmetries, the Hamiltonian functions used to have symmetries. And these symmetries used to destroy the Hessian of the function, the initial function, the Hamiltonian function on the world space. So applying stability methods directly on the initial problem was in many cases impossible, because you always rely on the Hessian and being non-degenerate and looking for eigenvalues or properties of the Hessian. But the problem is that in many cases it was so degenerated due to the symmetries of the Hamiltonian function that it was impossible. So this method was the only thing that was available. And this is one important thing. Is that it's not only that it is useful to go to the reduced submanifold. It's only that if you try to do it straightforwardly, you will not have no manner to do with it.
Exactly. And I mean, also the advantage is that it gives a way to compute these relative equilibrium points, right? Since in many cases it's very difficult. I mean, you have to reduce the whole system and looking for the equilibrium points of the reduced Hamiltonian system. And here you just the relative equilibrium points are not in general are not the equilibrium points of the initial Hamiltonian system, which is, so the energy momentum method gives a very nice way of finding and characterizing these relative equilibrium points. Thank you. So yeah, as I said at the end, I would like to comment on some applications and generalizations. I chose some of them, maybe not the most important ones, but important. So the energy momentum method admits many applications, many significant applications to like physical systems. There's also, I mean, the first application of the energy momentum method was to the rigid body, and this is like the most canonical example of the application of the energy momentum method. This method also allows for employing the so-called block diagonalization theorem, which even more simplifies the computation of stability of relative equilibrium points. There's also a generalization of energy momentum method to Poisson manifolds, which is called the energy Casimir method. Is based this energy Casimir method is based on Casimir functions, and basically when we want to, I mean, the energy Casimir methods just broadens the applicability I mean like it gives a lot of new options to characterize relative equilibrium points and studying the stability. In this paper, nonlinear stability of fluid and plasma equilibria, the authors just, I mean, they proved the energy Casimir method even for infinite dimensional Hamiltonian systems, and they apply for like real examples that find application in clouds, in very complicated fluid systems. There's also application to a time-dependent realm when we want to consider the Hamiltonian that is not preserved in time. We want to, you know, consider some kind of expansion of the body, which is called the pseudo-rigid body. And here the time is treated as a parameter. There is also a generalization to symplectic geometry when the time is considered as a variable on the manifold, and this also opens up a new opportunities since we can take into account the symmetries that possess the fundamental field has a term d over dt, so it gives like it allows for considering more general symmetries, and there are also generalization to the different geometric structure to, in particular, the energy momentum method for ordinary differential equations with K polysymplectic structure. There is much more generalization, and the energy momentum method can be applied in real physical problems when we want to look for relative equilibria and studying the stability of these relative equilibrium points. So this is what I wanted to tell you during this talk. So thank you for your attention.
Thank you, Bartosz. So, is there any other question, remark?
So, I have a comment. Perhaps in this method maybe extend to the contact setting. I seen in the case when you have a Hamiltonian and a standard Hamiltonian mechanical system, you pass to the hyper. You have a hyper surface. you can see in the symplectic manifold, you can see in the, if you want, in the cotangent bundle of a manifold, and then you pass to the level set of the Hamiltonian function, and then you have under some regularity condition, you have a contact structure here, and then suppose the standard Hamiltonian, the initial Hamiltonian system, the standard Hamiltonian system have symmetries, a Lie group of symmetries, and then it's possible to develop an energy momentum method in the hypersurface with the contact structure in order to obtain the relative equilibria for the rep vector field. In this case, the Hamiltonian vector field, the Hamiltonian vector field in the original symplectic manifold passed to the ref of the vector field of the contact hypersurface. In such a way, all the diagrams are commutative. Do you understand me? You can produce an energy momentum method for contact manifold, and then even if you want for rep dynamics, and then all the diagrams in the symplectic setting, in the contact setting, you can reduce, you can apply the energy momentum method for the contact, for the rep dynamics. You have another option. You can apply the energy momentum method in the symplectic manifold, and then you can pass to the reduced hypersurface, and everything is commutative. I don't know if it is possible because it is related with the problem of periodic orbit in Hamiltonian system. When you pass to the contact hypersurface, the idea is to obtain a periodic orbit for rep dynamics. But you can see, for instance, in relative periodic orbit. Do you understand me? You have relative equilibrium, you can have relatively periodic orbit. And this is important, for instance, for the Weinstein conjecture or everything. There are a lot of topics related with this kind of thing. Do you see?
Yeah. I know what you mean. And it's very interesting point of view. We wanted with us here and Javi, we wanted to devise the energy momentum method for contact manifolds. Like in general, we encountered some technical problems. But yeah, it's your idea is a little bit different. And it's worth thinking about it. So yeah, thank you. But yes, I know what you meant and what you were saying.
Well, Carlos, I will tell you. In general, we tried several things to approach, as Bartosz said, in the general setting. Yeah, and it's not possible to do it in the general setting and in the general techniques. For example, going from contact to symplectic and things like that don't used to work normally, because the problem is that, for example, with Janus approach, when you pick up one problem in the contact setting and you extend, normally when you extend a problem that down, it has a relative equilibrium or was an equilibrium, up it will not be of so, because you change the dynamic. Contact vector field with an equilibrium point, for example, when you put it up onto a symplectic, it does not need to have an equilibrium point. So it has additional stuff, yeah? There is no way to do it. Now, when you talk about this particular example, and that it's very important indeed, because I was working with red things and things like that lately, it is possible to generalize part of the stuff. I mean, as you said, you pick up a symplectic manifold. When you pick up a symplectic manifold, one of the things that it was found with Weinstein, it was that the reduction, the problem with the with a certain n sub certain hyper subphase, it turned out that the reduction to this hyper subphase was such that periodic orbits could be found if there is a related contact structure, something like that. So in this case, in this particular setting, some of our problems to find relative equilibrium points and things like that can be solved. But I will tell you that in contact manifolds, there are several technical problems to define the Hessian and to define certain structures, yeah? And the fact that it's an odd-dimensional manifold and you cannot how to tell you, it's quite technical.
Yeah.
I mean, we could send you something and you could see what is the problem, yeah? But it's difficult to me to explain you now.
Yeah.
The thing is that, for example, when you have not symplectic, but
the main problem is that we don't get the integrable distribution, but we don't have to deal with maximal non-integrable distribution.
We study, for example, co-symplectic geometry, yeah? And it was pretty easy because you have the time you have a symplectic manifold, you had a foliation, yeah? You can foliate the manifold. And it was pretty much easier to obtain the Hessian and to study the evolution in the reduced manifold thanks to that. But in contact, you don't have such a thing. You don't have a natural foliation with the red vector field or whatever. So it was difficult. So the problem is open. The case you told me is something worth of analyzing, indeed. We didn't think of it. But now that you reminded, it was like, come on, yeah, it could be cool. Yeah. But in general, we don't know how to deal with it. So thank you.
Essentially, I refer to this particular case when you have the contact hypersurface. I tried to solve the symplectic problem through a contact problem. This is my idea. It's not a general energy momentum method for contact geometry. I refer perhaps in a first step. I refer to this kind of problems.
Yeah, but you know, Juan Carlos, the point is that I noticed when we were doing this, that several subcases were interesting, could solve our technical problems, yeah? But I didn't find any mathematical or physical reasons to deal with any. But you have given us one, you know, this is the thing, one case that could be interesting.
Well, my motivation come from the classical problem of periodic orbit in a standard mechanical Hamiltonian system. When you try this problem, you transform the problem in a problem in rep dynamics. This is more or less the idea. So perhaps for equilibria, it's just maybe a similar situation in the case you can consider relative equilibria for contact for rep dynamics. This is more.
Indeed, Juan Carlos, I was working with Xavi, for example, with K-contact geometry. With K-contact geometry, K-symplectic that was studied partially by Sylvia, appears something similar to that you had certain, periodic with, multi-periodic solutions of a K-symplectic. They could be reduced to a K-contact manifold, yeah? And it turned out that under certain conditions, you can generalize the Weinstein conjecture to the K-contact thing. And it was things of that. So, and what you said about the studying with the contact, could be working with the K-contact, our K-contact problem, because we were also studying what you did with the dynamics with the red vector field transforming. with the K content. So it's very interesting indeed. I think that there are applications for the energy momentum method for a particular case, possibly, yeah. And even it could work also for generalizations for K contact geometry.
Yeah.
So it's cool. Thank you. Really.
Okay, thank you. Thank you for the comment.
Is there any other comments, question, remark?
Yeah, maybe just about one.
Yeah.
Also related to the discussion. When we study the relative equilibrium points, one has to be aware what kind of stability we get. For instance, on the reduced space, we can get that that the reduced relative equilibrium point is stable in a Lyapunov sense, but on our initial manifold, we get periodic stability. So it's indeed related to the periodic orbit and rep dynamics.
Yeah, it's also. And
okay.
also there is another thing, because in the case of symplectic geometry, you have a certain kind of Hamiltonian vector field, you have an energy momentum method. And when you go, for example, with contact or other structures, you will have evolution vector fields, you will have different vector fields that they are not Hamiltonian, or they are Hamiltonian in different senses. So for every one of these vector fields, you can think of a different energy momentum method. And sometimes the differences are important because they allow you to deal with problems that are not available in other manners. For example, in co-symplectic geometry, we have different types of Hamiltonian vector fields. There were gradient vector fields, there were Hamiltonian vector fields, there were evolution vector fields. And depending on the energy momentum method you developed with a different type of Hamiltonian or evolution or gradient vector field, the theory had different technical problems. Sometimes they could be solved, sometimes they couldn't. In contact is something like that. That you can have contact vector fields, Hamiltonian, yeah, you can these evolution vector fields. And depending on the sort, you can avoid certain problems, but normally others appear. But this is another thing that it can be used. Normally, it helps you solving approaching different things.
Yeah, I think that in contact geometry, the first option is dynamics.
Yeah.
Okay, thank you.
Thank you.
Thank you very much.
Okay, so thank you everybody for taking part in our seminar. And let me tell you that next week we have a talk about conservation laws for extended generalized Hiller-Kuramoto-Zivasky equations in any dimension by Pavel Hoba from the Silesian University in Opava. So see you in a week, and thank you very much.
Okay, see you.
See you.
See you.
Thank you, Juan Carlos.